This is lab 3 on magnetic fields and dipoles. The purpose of this lab is to understand the distance dependence of the magnetic field by a bar magnet, or how does the distance of an object impact the magnetic field, whether it's on-axis magnetic field or off-axis. Some of the concepts used were magnetic field and the magnetic dipole moment. And some of the results that I put down was the n distance dependence, as well as the predicted versus observed off-axis measurements. For the experiment procedure, I didn't have a meter stick to use here, so my alternative was that I stuck pieces of cardstock paper together and used a ruler to mark off inch marks. And then here is my magnet up here, and I also included boxes that represent my phone, as well as approximately where the magnetometer sensor was. For my experiment values, the important ones I decided to include were the average distance, the average x component of magnetic field, as well as the r and natural log component of both of those components, as well as the graph that shows that slope. And I also included my off-axis field measurement showing the perpendicular components measured. For my calculations, I used the slope equation to find the n and the natural log of k by using the slope of the graph to find n and the y-intercept to find the natural log of k. And for my slope, I found that n was equal to negative 5.716 or negative 6. Then for my natural log k, I got negative 21.276, which when mathed out, k would find to be 5.754 times 10 to the negative 10. So we're finding the magnetic dipole moment mu. I set the B dipole and the B bar equations together so I could use both the K constant as well as N to find mu. And I end up with this equation. And I added a table of the magnetic dipole moment for each field reading because I tried taking those values in order to take the average magnetic dipole moment at the end of it in amps times meter squared. For my code, one of the important things I made sure to use was I used the average mu for my calculations, and I used an important function called dipole B, which used the extended equation for B of a dipole, which is really helpful because the formula will pretty much know when the equation is on axis or off axis, and it'll really help with understanding and calculating those values. So after defining that function, then I define observation locations to easily find the r-axis and r vectors in order to easily find and use the dipole B equation to find the B fields, and then creating arrows off of that. And after finding those values, then I created and used my D perpendicular off-axis values. And as you can see in the model, the orange arrows are the on-axis locations. The cyan arrows are the off-axis calculations, or the perpendicular calculations. And then the magenta arrow is the off-axis of the 45-degree angle. And under that are all the values found in Teslas. So some important observations was that when the magnetometer was far from the magnet field approached zero in the x direction, and as it got closer to the magnet, it would almost exponentially increase in the x direction. My results seemed to almost double the predicted value in almost every location in my home, and I believe that some kind of interference in my home may be to blame for that issue. If the experiment didn't compensate for magnetic north, the values for magnetic field would change in the x direction, but the graph readings should have mostly been unchanged. And if two magnets were stuck together, the magnetic field reading would be much greater. So to conclude, the distance dependence, or n, my experimental value was negative 5.7156 versus negative 3, which you could tell from the dipole formula. The magnetic dipole moment was 5.0836 times 10 to the negative 11 amps times meter squared. And then the two vectors on the bottom represented the off-axis 45-degree angle magnetic field that I found. Thank you.